it looks like it's on my screen, so I guess everyone can see it.
Yeah. Okay. Yeah. I've got a thumbs up. So I can just advance the slides if you tell me.
Yeah, thank you. So yeah, we're switching gears. So first, thank you for the opportunity to present this work. I'm now going to talk about how clouds are crucial to capture Antarctic sea ice variability. But first, I want to show you this map of the radiative effect of clouds in the shortwave over the Antarctic. And you can see that the clouds reflect a lot of shortwave radiation over the sea ice-free Southern Ocean between 50 south and 60 south. This is shown by the bright and the white and light blue colors. And this is because the clouds are on top of a very dark surface, the dark ocean, and so they reflect, they are very bright and they reflect a lot of shortwave radiation back to space. So that's where the radiative effect is maximum. And then over the Antarctic and inside the sea ice, over the sea ice, you can see that this effect is much less. And that's because those surfaces are already bright. So whether or not you add an extra layer of cloud doesn't really change what's the amount of surface, the amount of shortwave radiation that is reflected back to space. And so here we're focusing on the Southern Ocean because this is the sea ice is really important there. It's affecting ocean circulation, and it's also affecting the surface albedo, as I just explained, and so that has a tremendous implication for surface temperature and warming in general. Can you go to the next one? Okay, so in the next slide, I'm showing results from Roche et al. 2020. And here they show that the CMIP models in general struggle to reproduce the sea ice area variability and trends. And this is a time series of sea ice area for the CMIP 40 CMIP models for the historical period in gray, and then for different emission scenarios in the future. And on top of that, you can see the observation in black. And most of the models do not capture that trend, that increasing trend, positive trend that's shown by the observations. And it's unclear from this figure, but they also do not really capture the variability of this trend. And so if they do not capture that, then we have some difficulty trusting what the simulation of the future should be. Next slide, please. So later on, Roche et al. 2023 focused on one particular model, the NASA GIS model E2.1, and they show that even when you try to nudge the wind in the model and also account for the meltwater, there is still some biases. So the model is doing a better job at reproducing the variability of the sea ice area, as I'm showing here, between 2001 and 2021. This is the sea ice area anomalies compared to the observations. So the wind nudge simulation in dark red is doing a better job at capturing the observation, but still you can see that some biases remain. But it's way better than the free running simulation, which has no nudged wind. And so the idea here is that we want to understand why, where those biases come from, how can we fix that? And so next slide, please. And so in another study, they reproduced this kind of simulation. Actually, it was before, but and so we can see that for a different model, the CSM1 model from NCAR, which is a CMIP model, this one, whereas the GIS model is a CMIP model. So we find the same, they found the same conclusion, which is when you nudge the wind, you get in better agreement with the observations. So on the right plot, so that's the dark blue line to compare with the black line, but there are still biases that remain. And so now we want to try to understand where those come from. And I also added a scatter plot on the right side of each plot, just to show that it's really clear that the dark dots which are the wind nudge simulations, are doing a much better job in terms of spatial correlation and spatial RMSE than the free-running ones. Next slide, please. So here I'm coming back to that map that I show you, because I'm gonna focus a little more on the shortwave radiative effect, cloud radiative effect, and I'm gonna show you that this is actually pretty famous, but the CMIP models do not really simulate the clouds very well over the Southern Ocean. Next slide, please. And so that's what I'm showing here. Basically, I'm looking at 9 CMIP 5 models and the same 9 CMIP 6 models. This is a multimodal mean, and that's the model minus the observation, which is the bias. And so you can see that over the red shaded areas, that's where there is more shortwave radiation coming through. So this is a warming bias on the surface. So there's more shortwave radiation that are trapped in the system, which result in a warming on the surface. And you can see that those biases are pretty important, substantial, on the order of -15 to +15 watt per meter square, which is, this is an annual mean, so this is quite big, also multimodal mean. Next slide, please. And here I'm trying to show you the same thing, but this is a zonal mean this time, a zonal mean of the shortwave CRE. And for 14 different CMIP 6 models, just to show you that there is variability, but they are always systematically biased against the observation. And mostly you can see that large biases over the gray shaded area, which is the sea ice free Southern Ocean. And that's where I'm going to focus the study. Most of the studies in the past have been looking at how biases over the sea ice or over the Antarctica could affect cloud biases or shortwave radiation biases could affect the sea ice. And here we're looking at we are putting ourselves at the edge of the sea ice, and we're looking at how biases around the sea ice, so at the edge, could affect the sea ice variability. Next slide, please. Yeah, so that's my assumption. So our assumption is that we are the biases at the edge, so the sea ice free Southern Ocean in the clouds could affect sea ice area variability. And so I'm going back to that time series plot instead, except that this time, instead of looking at the sea ice area anomalies, I'm looking at the shortwave CRE anomalies for those same 2 models, the NASA GIS and CSM1. And here again, we can see that the wind nudge simulations are capturing the variability of the shortwave CRE anomalies better than the free-running simulations, although it seems to be a little less clear for the NASA GIS model, but I'm going to show you in the next slide, please, that when you look at the spatial correlation and spatial RMSE, this is pretty obvious that those wind nudge simulation, which you see those dark dots, so dark red and dark blue, are doing a much better job at capturing the observation variability than the free-running simulation. And so one of the conclusions was that constraining the winds, in addition to improving sea ice variability, also produce more realistic variability in the cloud radiative properties over the Southern Ocean. Next slide, please. And so now we're trying to understand what is affecting, how can we improve that shortwave CRE even better, or what is the bias, where does the bias come from? And so basically we decomposed the contribution to the shortwave CRE in terms of cloud fraction and optical properties. And then we try to constrain each of these in the model with the observed one. So we switched the cloud fraction from the model, we used the observed cloud fraction, and then we did the same thing with optical properties to look at what kind, I mean, to better understand the origin of the biases in the shortwave CRE. And we found that when we constrain the cloud fraction in the model, we improves a lot more the shortwave CRE than when we constrain the optical properties. So that's shown by the dotted line, which is in better agreement with the dark black line, so the observation, compared to the dashed line, which is the simulation with optical property constraint. So the better correlation and better RMSE are found for the simulation in which we constrain the cloud fraction. So that's what should be fixed in the model to improve, first, to improve the shortwave CRE in CMIP6, at least in these two CMIP6 models. Next slide, please.
You're at 15 minutes now.
Okay, so then we wanted to, so I'm going back to those time series. Now I'm showing the sea ice area anomalies. Oops, one back. So the sea ice area anomalies and then the shortwave area anomalies. And we saw that there was roughly an anti-correlation between those two biases. And I'm trying to show that in a simple way with those blue and red shading. So you can see that a negative bias in the sea ice area anomalies correspond to a positive bias in the shortwave area anomalies. Roughly for the two models, it seems to match very well. So then we went into more detail, and then we computed on the next slide a scatter plot of these two variables. So the sea ice area anomalies as a function of the shortwave sea area anomalies, and we found that there is a very nice correlation between these two. And the nice thing to see here is that the slope is the same for the two models. That was surprising. And so a positive bias of 1 watt per meter square in the shortwave theory corresponds to a negative bias of 500,000 kilometers square in the sea ice area in both of these models. Next slide, please. And then we wanted to see how we could translate this for the CMIP6 models. And so we looked at 12 CMIP6 models, and we look at the trends in the shortwave theory anomalies, which was easy to compute from the CMIP simulations. And then we translated these biases in the trends into sea ice area changes using that slope that we found for the two models. So we are assuming that the relationship is the same. The relationship between sea ice area and shortwave theory is the same in the CMIP6 models as it is in the GIS and CSM1 models. And so when you do that, you can infer what would be the change in sea ice area, and that's what we found. So in most models, 10 out of 12, we found that shortwave theory anomalies contribute to enhancing the sea ice area loss during the historical period. Next slide, please. And that's my summary. So we constrained the winds. We found that constraining the winds produces more realistic variability in terms of cloud radiative properties over the Southern Ocean and sea ice area. Then we showed that constraining the cloud fraction improves the shortwave theory variability more than just constraining the optical properties. So the cloud fraction is the real problem, it seems, in the models. And then we found that if we were to fix those shortwave theory biases in the model, that would affect the sea ice area. And so just fixing 1 watt per meter square bias in the model would correspond to a negative bias of 500,000 kilometers square in sea ice area. And that would, it seems like that would have a tremendous impact also in the CMIP6 models. Thank you.
Thanks, Greg. Is there any questions? Anyone got a question they want to ask? Don't see anything in the chat. I've got a question regarding that second point there that you've got on your summary slide. You said that constraining the cloud fraction obviously makes a big improvement. So, what would be the way forward to fix that cloud fraction issue in the models? Then is that something to do with a lack of observational data, or is it another factor?
Oh no, the data we have. It's likely another factor. I mean, the parameterization, it's a very difficult area because There's a problem with dynamics, parameterization of the clouds. There's so many things going on right there. So it's not as simple. And there's also the fact that we have the microphysics is also something problematic because there's a lot of super cool liquid clouds in this region, and they can go higher than where we expect them. So they can be in the middle troposphere and not just in the lower troposphere. So that's a very difficult location for clouds and for the models. But there's room for improvement, and we have a lot of data to work with.